Afternoon, everybody. Also is at home. So first thing of this week, we are going to solve the exercise assigned last week. So I just remind you that we introduced the centroid of forces, taking a set of concentrated forces GI that you have in your notes. Centroid of forces here. So we had a set of N forces called GI. And given these forces, you could find the centroid of forces. So first of all, the resultant force, G, the force which is the resultant of all the forces, and the centroid, which is the point in which we can apply the resultant force without changing the effect of all the forces applied to the system. So basically, we can substitute all these GI forces with one single force, which is the resultant force, applied on a specific point, which is called centroid. The centroid's coordinates can be found through these equations, which are basically a weighted mean or average, if you want. So these equations are valid for discrete forces. So forces that you can see as set of separated concentrated forces. So G1, for example, 10 kilonewtons, 2 kilonewtons, minus 10 kilonewtons, and so on. But in case we have line loads or distributed forces, as it was the case of the first example that we have here, we need to use the integrals, because the integrals, so instead of the sum of discrete elements, so discrete forces in this case, concentrated forces, we need to use the integral, okay? So in this case, it was quite simple because we had the line load, uniform line load, uniform for all the beam length. But in this case, so for the exercise that I assigned to be solved at home, we have a triangular distribution. So the simplest thing to do is to fix the axis origin into O, which is the first node, the node on the left hand, which we will see today. It's a hinge or a roller. We will see supports today. And then the second thing is to write down the function of Q variable with X. So Q is basically variable with X. And this is the most important thing to know, because then we have to write down the integral. So first of all, in this case, the centroid will be in some point of the beam. So if this is our beam, the centroid can be, for example, here, C1, C2, C3. Where is the real centroid? That's the point. The centroid of the triangular force distribution. So the centroid depends on the force distribution in this case, because we are talking about centroid of forces, but we will see that we'll have also geometrical centroids. Bless you. So we'll have different kinds of centroids. In this case, we are talking about centroid of forces, okay? So what is the real position of C? First of all, we need to write that xc is equal to integral of what? X, the generic X times Qx. So it's like to write down the static moment. So on the numerator of this formula, we have the static moment with respect to the y-axis. This is y, and this is x. In the x, because x is the variable coordinate, all divided by what? Let's see the formula. The formula you see, you have the static moment with respect to y, which is this one. This one is also called static moment. Why with respect to I? Because x is the distance of a generic point from the y-axis. You see here, for example, the generic distance xi, this one, is the distance from the y-axis. So this sum of gi times xi is the static moment of the gi force with respect to the y-axis, because xi is the distance from y. Because the distance of any point from y is measured through xi. And at the bottom, we have the resultant force. So this is the resultant force of the forces. Of course, it's absolute value, so it's the module, okay? So the magnitude or the intensity of the force vector, because we cannot divide something by a vector. As you remember, yes. Because it's the opposite, because x are the distances from y. So it's like a convention. And if you are doing the static moment with respect to x, you will have to consider the y distances in terms of y. It's like dual, let's say. So I was saying that being R or any force a vector, we cannot divide something by something which is a vector, but something which is a vector intensity or magnitude. So that's why I wrote just the absolute value. So the two vertical bars, as you remember from last week, they indicate the magnitude of a vector, okay? Is that clear for everybody? Yeah? Also from home? Okay, good. So I was saying that then we have to divide this formula by what? By the magnitude of the resultant. So the resultant will be integral of qx in the x. And the two integrals have the same limits, so they go from 0 to what is the distance, the beam length? What is the beam length? L. So the integrals go from 0 to L, the two extremities, the two limits of the integral, and we have the same in the numerator. So we need to consider the whole load. The load is going from 0 to L. the triangular load distribution is going from 0 to L. If the load distribution were going from 0 to L half, for example, instead of L, you had to put L half. Clear? So you have to consider what is the load distribution. So if the load changes, of course, this integral will change. So now we can solve this integral. So first of all, let's solve this one. So the resultant, the denominator. So the resultant will be integral from 0 to L qx in the x equal to, I've just copied the previous expression, the denominator. So qx, as you remember, it was expressed as, I told you last week, x divided by L times q. Because for x equal to 0, 0 is the load. And for x equal to L, q is the load. Very important to know, q, small q, is expressed as, what is the unit of q? Small. It's a force divided by length, because it's a line load. Also tomorrow there will be some questions. Yeah, correct, Orkan. Thank you so much. But newtons are in a capital letter always, so never small, okay? Meters, yes. So also tomorrow there will be such kind of exercises. So if it's not clear that a line load is a force divided by length, please give a look at that, okay? Similarly, the concentrated force, what unit does a concentrated force have? Yes, Newton or kilonewtons, whatever, decanewtons, okay? And what about a volume force? What is the unit of a volume force? Kilonewton divided by cubic meters. Exactly. Because a volume is measured in cubic meters. So the types of forces are very important in structural design. So it's better that you have very clear this concept. Thank you also, Marzi. It's correct. It's cubic meters. So the resultant force that will be, we can write down Q divided by L times X, which is Q, times dx. So Q divided by L is constant, and therefore we can put it before the integral, out of the integral. And inside the integral, we'll have integral from 0 to L times x dx. This is equal to Q divided by L. Now the integral from 0 to L of x in dx, do you remember the rule from the high school? These are high school topics. I want to highlight this. These are high school topics. Unless you have done humanistic studies, as in my case, but I guess that you as architects, you have a bachelor degree, right? All of you. Who doesn't have a bachelor degree? All of you. You don't, but you have done something for, okay, so, but you know, math, integrals, okay. In any case, it's, I mean, something which is, which you should know, okay? So the integral is x squared divided by 2, because you have to increase the exponent of x and you have to divide by the same number. And we have to compute it from 0 to L. Okay? Yeah. This line means that you have to compute from 0 to L. It's like a convention. Now you will have it more clearer, like Q divided by L. This line means that you have to write this one as, first you substitute L in X, and you have L squared divided by 2, minus 0 squared divided by 2. So this is a translation of this line. Of course, this number is equal to 0 because 0 square is 0. And therefore, you have QL divided by 2, which is the resultant force. Yeah. No, you'll have the notes. You can see your notes. And it's without grade, okay? So tomorrow it's just a test for yourself, not for me. Just understand what is your point. Okay. And this is true that it's the resultant, because if we have a look at this triangular shape, maybe it's better to close some window. We have that this is a triangle, okay? So this is, the length is L. And the resultant force is, of course, what? The area of this triangle, because it's a resultant. So the area of this triangle is equal to QL divided by 2. Because it's also, and this is also the magnitude of the resultant. So you don't need to refer to integrals, which sometimes are very difficult, but it's very simple because you can understand that the resultant force is actually an area. Okay? Very simple. Now we have the denominator. So this part is known at the moment. So now we want to find the numerator here. So we want to find the integral from 0 to L equal to, of x times qx dx. We just substitute the formula qx, which is q divided by L times x. Sorry? This one is the numerator of this formula here. This one. Okay? So we are now solving this. Okay? Okay, so this is equal to, so q divided by L, we can put it before the integral because it's a constant. Integral from 0 to L of x squared, in this case, dx. Now, this is equal to Q divided by L. And this integral, if you remember, again, you have to add 1 because I just write it. Integral of xn in the x is equal to xn plus 1 divided n plus 1, with n belonging to natural numbers. So this is the general formula, math formula. So since we have integral from 0 to L, x square dx, what is the integral? X exponent 3 divided by 3. So, and this must be computed from 0 to L again. Because it's 2. So 2 plus 1 divided by 3. This is equal to Q divided by L times, again, L exponential 3 now, minus 0 is clear. And therefore, the numerator is QL squared divided by 3. Okay. Now we can write the final formula because the x coordinate of the centroid will be QL squared divided by 3 times 1 divided by QL half. Okay, from the formula. And we can write it like QL squared divided by 3 times 2 divided by QL. So now Q and Q are the same, so we can divide everything by Q, L and L. So the final result is 2/3 L. Okay? So let's draw again this beam. This is the triangular load. So these formulas tell us that the centroid, so if we want to completely substitute the load, triangular load, with a concentrated force, a resultant force, we have to know, since a force vector is defined by magnitude, direction, and point of application, as seen last week. So we have the magnitude, which is the resultant. So R is equal to QL divided by 2, which is the area. And the position is at 2/3 of L. From 0, so from the axis origin. So you have to check what is 2/3 of L. That will be somewhere here, for example. This is 2/3 of L. And it means that your force will be here. So this will be your resultant force. Okay? And do you remember if I give you a triangle, rectangle, triangle, so a triangle in which, or no, in general, a triangle. Where is the centroid of this triangle? Yes? Intersection. Intersection. Yes, exactly. And yes, it's correct. You have to take the half point, then you have to connect the elements. You said that, right? So this is the centroid, yes. And, but apart from that, the centroid, if h is the height of your triangle, this point, or if you prefer, this point will always be at 2/3 of your height. And the part down here, 1/3 of height. So if you look at this triangular load distribution, basically it's correct that your centroid is at 2/3 because the point will be actually it will be at 2/3. So this will be, this distance from the origin will be at 2/3 of L, if L is the height of your triangle. So as you can see, yes, thank you also Ain who answered, and Rahaf also, who answered correctly the question. So actually, it's just a matter to find the resultant force, R, with the area of the triangle, and the position of the centroid, of the geometrical shape. The geometrical shape defined by the load itself. Let's check the dimensions, which is always really important. So the resultant is QL divided by 2. So Q, what unit is Q? In, for example, in newtons divided by meters. So newtons divided by meters times 2 is dimensionless, of course, and L, meters. So the result is newtons. Correct, because R is a concentrated force, and therefore its unit is a newton or kilonewton, a force in any case. And what about XC? What is the unit of XC? Meters, it's a length. So it's being a length, its unit is a meter. And indeed, 2/3 of L is a meter because we have just the length. Therefore, the dimensional analysis is correct. And you have always to make this check, because this is a check which, without any doubts, confirm your result or not confirm your result. So you maybe have to look better. Okay? Do you have some questions? No? Yes?
We have to all the integration. We can just give you the area of the triangle and then
Yes, yes, of course. Yes. For example, if I give you these numbers, I give you this beam, and I tell you that you have a beam with a, oh, let's change. I give you this load distribution. Okay. And this Q first. And L first. I give you, for example, Q first equal to 8 kilonewtons divided by meters. So you have a beam with this Q, applied Q. And length, L first, of 4 meters. So you have a beam of span, beam length 4 meters. Then you just find, and you are asked to find the resultant. So I ask you, find the resultant of this force. The resultant will be, so QL divided by 2, so 8 times 4 divided by 2. 16, yes, Samirezza, thank you. 16 watt. Always put the unit, so kilonewtons. Okay, and the centroid XC, now you have to be careful, because you see that now if you define, if you choose this point as origin, as before, then you cannot write anymore QX equal to QX divided by L. This is not correct anymore. So it will be a different load, a different Q function. So in order to have the same Q, you have to fix your axis origin in here. Okay? Otherwise, it will be different. It's possible also to solve with a different QX, but it's complicated, useless. So since you know that you know how to solve it, then it's clear. So you know that XC with this correct position of your axis, so with the the origin on the right end, right support, it will be 2/3 times length. Length is 4. So it will be around 2 and something. So we can keep it 1/3 meters. So it will be somewhere here. Basically, you can divide it by 3. So this is 1, 2, 3, and you take 2/3. So this will be the precise point of your resultant, a point of application. This will be at 2/3 of L first. Okay? So now there is a question from Darin and another one from Raf, which are the same. Darin asks, I was planning to ask if it's okay to solve it as a geometrical approach, since in my bachelor classes we use that. And if I solve those with geometric way rather than limit, I would lose any points. It's always better to solve these problems with letters. So to be more general, okay? So as we generally, I will solve things using letters, and then we will make numerical examples, as in this case, which is much better because knowing the general answer, then you can use it for all the numerical cases, but not vice versa. Okay? Is that clear, Darin and Rahaf? Okay, perfect. You're welcome. Okay, so do you have any questions about, yes? Two divided? 2/3 is valid whenever you have the triangular shape and the origin at the at q equal to 0. Otherwise, you can also solve it by putting your axis origin on your left support, but the expression will be different. The expression will be like q. There is no need to know, but just if you want to check it, it will be q equal to q L minus x divided by L. Because for x equal to 0, it will be q. Okay, q first if you want. Okay, and for x equal to L, it will be how much? Or L first, better. If you substitute L first in this expression, how much it will be? 0. So the only thing that changes is the function. So as a function, then you'll have to write, for example, integral from 0 to L first of this. Q first, L first minus x divided by L first dx equal to blah, blah, blah. And you'll have the same result. You can check it if you want. So you'll have exactly the same result. The result will be 1/3. So xc in this case will be 1/3 of L first instead of 2/3. Because the resultant force, the point of application, is always in the same point, but depending on your reference starting point, it will be different. Okay? So there is no need to complicate things when they are already simple. So it's better to be smarter and fix your point in the simplest point and simplify as much as possible the load distribution instead of changing the point. Okay, now if there aren't any other questions, then are there other questions? Otherwise, we take a break. Other questions also for tomorrow? You should bring your laptop, yes. No, we are going to do also a class, short class, yes. And so also be sure that you are registered on Moodle, because at the moment I see 86 participants, but you should be 100, around 100. So some of you probably is not registered yet. So please be sure that all of you are on Moodle. Okay, see you in 15 minutes then, at around 2:05. Introducing a new topic, but very similar to the previous one, basically the same. The thing that changes is that we are considering now geometrical shapes instead of forces. Let's see why it's not working anymore. So centroid of forces. Now we have centroid of areas. Okay. Was it blinking before? Like this? Was it blinking, the screen? No? Okay. We are satisfied with that. Let's take a very simple geometrical shape, which is a rectangular shape. So we have this rectangle. Whose dimensions are B and H. B is the base, H is the height. And O is the axis origin. X is the horizontal axis and Y is the vertical axis. So we want to find the centroid of this geometrical shape. So XC and YC. And again, as we did earlier, we are going to use the same formula. So the formula is the static moment with respect to the y-axis, in case of XC, divided by, instead of the resultant force, we have the area of the rectangle. So since we are dealing with geometrical shapes. We are not dealing anymore with forces. We are dealing with geometrical shapes. So A is the area. And similarly for YC, we have the static moment with respect to X divided by the area. So what is the static moment with respect to Y? Again, since the geometrical shape, the rectangle, is a distributed surface, let's say, it will be that the integral over the area. By definition, this is the definition of static moment with respect to y-axis. How can we find the static moment? The static moment is this. Look, you take a generic strip of width. The width of this strip is dx. So the static moment is the sum of each strip of area dx times h, so each strip, multiplied by its distance from the x-axis. So this is the generic x, this is x, and therefore this distance is x. Just to be clearer, if you have like masses, for example, mass M1 concentrated in 2 points, M2, M3, okay, and you have coordinate axes, for example, X and Y, the static moment of these masses with respect to Y is the product. So first of all, you make the product of each mass. So it's Mi times what? The distance of each mass with respect to the y-axis. So this will be y1, this will be y2, and this will be, x1, x2, and this will be x3. So what do? You take each mass, so Mi, and you multiply it by the corresponding distance from the y-axis, and you make the sum. The sum for I going from 1 to 3, because in this case you have 3 masses. For example, let's make a numerical example. M1 is equal to M3, which is 2 kilograms, and M2 is equal to 1 kilogram. Okay, it's just a numerical example. The 3 distances are x1, so they are given, they are known, okay? So x1 will be, for example, 2 meters. X2 will be 3 meters. And x3 will be 1 meter. Okay? So the static moment with respect to y-axis, so Sx, by definition, will be the product of each mass times the corresponding distance from that axis, so y-axis, and then you make the sum of these three products. So it will be m1 times x1 plus m2 times x2 plus m3 times x3. So this will be the static moment of the masses. Okay, so m1 is 2 kilos, 2 times x1 is 2 meters, plus m2 is 1 kilo times x2 is 3 meters, plus m3 is 2 kilos times 1 meter. So in total, we'll have 4 plus 3 plus 2. So 9 kilograms times meters. And this is the static moment of the masses with respect to y-axis. So this means the sum, this sum. The same concept we apply is applied for geometrical shapes. So coming back to the rectangle, this time we don't have discrete areas. We have an area which is continuous, let's say. So the static moment will be each strip of, so the area, the single area will be h times the x. So this is the strip area, let's say, times x, which is the distance from the x-axis, y-axis, sorry. So it's absolutely the same. So it's just in terms of static moment. And the integral must be made from 0 to what is the maximum x? Because x goes from 0 to this maximum, but this maximum is b. So this is b. So the integral goes from 0 to b because x varies from 0 to b. So instead of adding discrete elements like the masses that we've just seen together, you take small strips, one close to each other, along the horizontal axis. Okay, and this must be divided by the area. What is the area of the rectangle? Exactly, BH. And again, down. This time, we have just to change the letters. It's very simple for the static moment. With respect to the x-axis, now let's look before we have a look at the static moment formula. We have the integral of, now the strip will be in perpendicular direction. So we'll have to consider this strip where the variable element is dy. And the length of this strip is fixed and equal to b. So this time the strip is moving in vertical direction. Before it was moving in horizontal direction. Now it's moving in vertical direction. Clear? Okay, so integral of, what is the area now of this small strip? Please tell me. B times dy, perfect. And what is the distance of this area? Y, very good. And what are the extremities of the integral, the limits? 0 and perfect. You see, very simple. Once you understand the mechanism, then everything is simple. And is divided by A, which is again BH. Yes, a pair. Also, you are right. So now we continue. Now we take these equations. We move them here. Xc is equal to, we said, integral from 0 to b. Now it's better to put always dx at the end of the integral. So we have xh dx divided by bh. Now h is constant, so it can be put out of the integral from 0 to b x dx, and everything divided by bh. So now we are good with this integral because we've just seen it 1 hour ago around. So it's integral of, instead of the integral, we just modified x exponential 2 divided by 2, perfect, between 0 and b. This divided by bh. So now h, so it's very simple because it's b squared divided by 2 minus 0 squared divided by 2, which is 0, times 1 divided by bh. And this is equal to b squared h divided by 2bh. Now we can simplify. H and H go away, and B go away as well. So we have B half. It's a length, of course. So it's, for example, a meter or a millimeter also. It can be both. Now, YC, the centroid, in considering the vertical axis, so it will be integral from 0 to h of what? by dy. I'm just copying what it's written at the top. Divided by bh. This time b is constant, so I can put it outside the integral. Integral now from 0 to h of y dy divided by bh. Actually, still we can simplify the 2b in here. And we have epsilon squared divided by 2 from 0 to h, which is the upper limit times 1 divided by h. So it's h squared divided by 2 minus 0. And everything is divided by h. So the result is h half. Yes. H half. It's absolutely the same as before. Okay, nothing changes. So all this to say that if we have a rectangle, so a planar surface with vertical and horizontal axis y and x and base b and height h, where is the centroid? In the middle. So is it true what we have found? Yes. So it's just a confirmation because we know that, of course, to find the center of a rectangle, the centroid is this one. So the distance from, so for example, YC is equal to H half, and the distance from Y, XC, is equal to B half. So it's a confirmation of what we already know, but by using static moments and the formula for centroids. Now Seper asks, what about other shapes not rectangle? You have to follow the same procedure. So basically, for example, for triangular shapes, for example, you fix your, I won't ask you complex shapes, okay? I will just ask you simple things. Also triangles just for loads, not for this kind of things. But since this is a question I want to answer. So in this case, for example, your centroid will be here. So again, you have to write down XC and YC like static moments again. So for example, SY of this, in this case, it's a triangular shape, this one. So SY divided by the area of the rectangle, which will be BH divided by 2 if the height is this one and B is the base of your triangle. And for YC, you will have the opposite. So SX divided by A. So absolutely, you see the same formula. So always the static moment divided by the, in terms of areas, okay, divided by the surface. And by the way, for example, you will find that YC will be H third, because we've already seen it, that it's 1/3. The distance from the x-axis in this case. And the same will be for the y-axis. But with this distance in this case. Is that clear, Seper? Not answering. Yes, okay. Okay, so why do we need these strange formulas that you need to learn by heart this for the midterm, this formula? It's very simple because once you make a numerical exercise, you have it in your mind. You don't need to remember it anymore. Because it may be possible that you are asked to find a centroid of a facade. For example, a masonry facade. Let's take this example. You have a masonry building facade like this. And you want to find the centroid of, so this is an opening, a door, for example, and you want to find the centroid. So if this opening was not here, so if this was full, so the centroid was simple to calculate, would have been simple because it was the intersection between diagonals. But in this case, you have this opening, and so you have to consider it. So probably we have the measures, so the height of your facade. And then you have all the other dimensions. So you have L1, L2, the opening, and L3. And also you have these two dimensions. H1 and H2. So a possible question is to find the centroid of this, for example, masonry facade, given all the values H1, H2, L1, L2, and L3. So just a centroid position. You don't need any other datum, any other. It's the sum, yes. Yeah. Also H is the sum of H1 and H2. So you don't need any other values because, yeah, probably you can say, yeah, I need the thickness of the facade. Yes, of course, but we are considering, we want the centroid position just on the facade itself. So one thing, for example, since it's symmetric, one thing that by intuition, because in structural engineering, we use very much intuition, a lot, to simplify issues. So you don't have to focus too much on the use of strange formulas. I mean, you get crazy. No, you have to go by intuition. So since this is a symmetric facade, is this symmetric? Yeah. So we already know that the centroid will be somewhere in this axis. So it will be either here or here or here. I don't know where, but somewhere here in this axis, thanks to symmetry. But let's assuming it's not symmetric, so that in general L3 is different from L1. So we want to be as much general as possible. So L1 is different from L3, so not symmetric. So we have two paths to follow to find C. And again, as we saw last week for forces, these two paths must give the same result. So you can use one or the other as a check. Okay? So It's very simple and very nice because it's something, if you understand, you can apply it very easily and very fast. So let's take again the axis origin on the left corner and the two axes. You see how much to put the axis on a geometrical shape is important, is relevant also for forces, because we need to put things in the space. So we need to fix a reference system. This reference system must be fixed. And this reference system is X and Y in this case. So look, we can see this shape as composed as three areas. One is this one, area 1, A1. The second one is, oh, let me see. The third one is A3. Let me use another color, okay? Let's use this color. And the second one is this one. So we just remove this. A 2 seconds. Okay? And each of these areas will have a specific distance, the centroid of each rectangle, which I know how to compute because it's simple. It's like the half base and half height. So I know the distances from the axis. For example, for A1, C1 will be this one. So the distance, for example, from the x-axis will be, I know it already, h1 divided by 2. And what is the distance from the y-axis? Very good. So L1 divided by 2. Also, I know the distance from C3 because yes, there is a mistake in here, and you didn't told me is h divided by 2, not h1, because h1 is just the height of the opening, okay? So this is h divided by 2 again for area number 3. And what is the distance of C3 with respect to the y-axis? Let's see. It's, let's see, L1 plus, yes, very good. This is the distance. So we already know the centroids of these rectangular areas. We don't need to make integrals or difficult stuff. We know already. And the same will be for C2. For example, the height of C2 will be what? Perfect. H1 plus H2 divided by 2. Exactly. Yes. The general formula, yes. But for the midterm, for example, I will never ask this. I will ask, but I can ask like rectangles. Okay, so to me, it's important that you understand the concept, not the formula. Okay, if there is a formula to remember for the midterm, I will give it to you. Okay, and what is the distance of C2 from the y-axis? Yes. Perfect. So we have everything now. Of course, you can choose to translate your axis in the middle of the facade, for example. It's not said that you have to put it on the left bottom corner. You can move it. The result will be always the same. So now you want to find the centroid. The centroid probably due to the fact that we removed the opening portion, it will be upper than the previous one. So it will be probably here, the centroid. And the formulas are, let's go for XC. XC is the static moment with respect to Y divided by the total sum of your geometrical shape. So the total. So basically, let's start from SY. As we said, for SY, we have to take the sum for the I areas, which are how many in this 3? Perfect. So AI, the area, times the distances of the centroids of each area from the y-axis. So XCI. So XCI is the distance of the eyes centroid, eyes area centroid, from the y-axis. Clear? For everybody? Once again? So XYC, for example, I write XC3, okay? XC3, you told me already, so you know it already. So XC3 is L1 plus L2 plus L3 divided by 2. This one. Okay, is the position of the centroid of each area. And what is YC3? No, YC3. Exactly. H divided by 2. Okay, now? Clear? This. Because each centroid is like a point with coordinate X and Y. Yes. According of each centroid of each area, you take the coordinate. So coming back to the formula, then with a numerical example, it will be even simpler. So you have now to sum up all the areas that you have. And YC, it will be the same. So SX divided by A equal to sum, this time AI, but times XCI, YCI, because have to take, to change, divided by sum of all the areas. So let's write these two formulas with our general formulas. We write these formulas for this example. Okay? So we have XC. XC is A1 times XC1, so the X coordinate of the first area, of the centroid of the first area, plus A2 times XC2. So you have like any rectangle area times the corresponding centroid, the distance from that axis. Sum of the AI, this one, yes, I just write it, okay? So SY is the sum of the products of each area AI times the distance of the centroid of the same area from the y-axis. AI is the ith area. So AI can be the first area, A1 or A2 or A3. Okay, so I is used just to not to refer to a specific area, but one of the three in general. So this is by definition. So let's come back to XC then. It's important that you all understand. So if you have some doubts, just ask. So then we have plus A3 times XC3. This is the sum of the products of each area AI, A1, for example, times XC1 plus A2 times XC2 plus A3 times XC3. So indeed, it is the sum of the products, right? And this divided by what? A1 plus A2 plus A3. Now, I want that you tell me YC. What is YC? A1 times, perfect, plus Yes. Yes. Times. Okay. Divided by plus. Okay. You see, it's absolutely the same. Let's see a numerical example. Okay? Yeah. Yeah.
We are going to buy, my calculates the centroid of the wall and
Yes.
dividing the smaller parts.
And then subtracting the smaller part, the opening. Yes, we'll see it in a while. Yes, it's another way to calculate it, simpler. Okay. Okay, so let's make a very short numerical example, okay? So this is, for example, 2 meters, 1 meter, 2 meters. This is 3 meters. And this is 3 meters as well. So all is given in meters. This is 1. This is 3, for example. And this is 2. So we have X, C. A1. A1 is 2 times the area, first of all, the area. 2 times 6, yes. Because 6 is the height and 2 is the base. Times the centroid XC1 is perfect. 1, because it's 2 divided by 2. Is here, the centroid 1. Now, A2, 3. 1 times 3. And 2.5 exactly. 5 half. Plus A3 is, again, 2 times 6. Exactly. And XC3 is 4. Very good. All divided by, what is the total area? So we have 2 times 6 plus 1 times 3 plus 2 times 6. And this is the numerator is in square, square meters, and the denominator is in meters. So meters is XC. So we have 12 times 15 divided by 2 plus 48. 12 times 4, 48. Divided by 24 plus 3, 27. If I am right, 27. So here you have 2, here you have 24 plus 96 plus 15, let me write it properly, plus 15 plus 96. And this is times 1 divided by 27. So again, 24 plus 96 is 120. So 135, if I am right, divided by, this can be divided by 3. 3 divided by 3 is 9 here. And 45 here. Again, divided by 3. Oh, sorry. So it should be 15 divided by 6, if I am right. Right? Is that right? Sorry? Yes. Yes. Right. 2.5 meters. Yeah. Yes, yes, yes. It's possible. I will show you later how to do that, and it's a confirmation of the correctness of the procedure. This is the general procedure, okay? Then there is the smarter procedure that you are saying. So is it, in your opinion, is it correct that we have this 2.5? Yes, why? Exactly. It's symmetric. So if this is the, oh, if this is the symmetry axis, then it's clear that this distance must be 2.5 meters. So even without wasting time in calculating that, it was sure that it was 2.5 meters. Okay. Now, YC, calculate as an exercise at home. And how to see if it will be correct or not? There is a second way to make this calculation smarter, as I told you. And this way is this one. Look. So we can see this facade. Then we make a break, take a break. We can see this facade as like equal to the entire facade, but without this opening, basically. So we could see it as the total area of the facade, which is A. So if we fix dimensions, maybe it's better. So this is like, we call it H, and we call this B, So the total area is B times H, and this is trivial. And we can play with static moments in order to have the final centroid by considering the removed area, so the openings area. We call it B, small b, and small h. And we call this A opening. So A opening will be B times H. Therefore, XC now will be the static moment of the whole area with respect to SA, with respect to Y always, minus the static moment of the opening, again, with respect to the Y-axis. So the Y and the X-axis are already there, divided by what? A minus A opening. Exactly. Because you have to, because you are subtracting that opening. So that opening is less, is removed from the total area. So again, for YC, you have SAX minus SA opening Y, sorry, X. It's just a matter of changing the letters. And the denominator is the same. So is A minus A opening. Clear? So an exercise that you should put also in your portfolio will be solve the same as exercise as before with the second method. And compare the results. Of course, the results must be the same. Otherwise, there is a mistake. And clearly you can have much more complex situations. So in real cases, of course, you won't have one opening and one window. You will have many openings. You will have like one door, maybe, I don't know, 3 windows in different positions, hopefully on the same line, but architects, generally they move windows, you know? So you'll have displaced everywhere without any symmetric disposal. So we'll have, for example, opening 1, opening 2, opening 3, opening 4, and so on. And the results will always be the same. So the X centroid will be the sum of all the whole area. So SA, where A is the total area, minus the sum of all the openings AI related to the openings divided by the full area, because A minus the sum of the openings is the area which is full. So the full area is basically the purple one, this one, because you are removing all the openings from the full area, which is B, capital letter B, times H, capital letter again. Here something is missing. X times XCI. Okay. So this is the sum of the static moments of the openings with respect to Y. So it doesn't matter to write every time S, X, S, Y, it doesn't matter to me. The important is that you refer to the correct axis. So if you are doing the calculation with respect to the Y axis, you will use X. If you are doing the calculation with respect to the X axis, you will use Y. Always the distance. And just for completeness, and then we stop. YC is equal to SAX minus sum of SAI X divided by total area minus sum of the openings. So that is valid in case we have many openings. This is, of course, the easiest way, because if you proceed with the first method, it will be very long, you know, probably impossible, because if your openings are not aligned, then it's very difficult to do it. Yep. Which one? Mm-hmm. Yes, it is Y. Ah, you mean XCI? No, it's XC. Because it's the distance, as you have it here, is the distance from the Y-axis, but is C. You see here. Y, yes. Yes, it's the static moment. You can express it also with the sum AI times YCI. Okay? Okay, let's take a break, 15 minutes. We start at 3:25. So let's have a very brief discussion about the last time exercise that I assigned to you. Many of your friends asked me some clarifications. So I think it's useful to give you this explanation as well. So the exercise was this one. So basically we had this elements. We had a weight here connected with the rigid element to the node B. So this block was fully rigid. And we had these two structural members. These are called truss elements. They can be subjected either to tension or to compression. We call them, as you remember last time, ties or cables, and rods for compression elements or truss elements. And you were asked to find F1 and F2. So the two unknowns were F1 and F2, which are the forces in the elements AB and BC respectively, so in the two elements. And you were asked to find the magnitude, because the direction is already known. So the direction, because alpha and beta were given. So the only unknowns were F1, the magnitude, and F2. So these were the magnitudes, the unknowns. All the rest was given, also W was given. Okay, just delete everything. I explain it again for all of you. So the first thing to know is, if you don't know anything, you proceed with the equilibrium conditions. So the as you know, because the equilibrium conditions in this case are sufficient. So the free body diagram is this one. So you have the node B. In node B, you have the weight W. And then you have the two forces, F1 and F2. In principle, you don't know if F2, for example, is like this or is like this. You don't know it. So you know the direction, but you don't know the, the line of action, but you don't know the direction. You don't know the verse. You know only the line of action. The same is valid for F1, for AB. So let's assume we take wrong directions, okay? So for example, we take, for F1, we take this direction. This direction means that AB is compressed. So an arrow that goes into the node means that that element is compressed. An arrow which goes out from the node means that that element is in tensile state. We saw it last time, okay? So let's assume we take this F1 and F2 is compressed as well. So let's assume that AB and BC are both compressed. So we have F1. I'm writing down the free body diagram, okay? And F2 will be like this, for example. And you write so the free body diagram is that one. Okay, this one. And now you can understand if it's correct or not. I tell you, it's not correct. And you can understand it very easily, because if you write down SFX, so the sum of forces in X direction, and SFY, the sum of forces in Y direction, we fix, for example, X and Y directions like this. So this is the horizontal direction and Y is the vertical axis. Why it cannot be true? Because if I write, for example, in the horizontal direction, the translation, which is the first one, I have to write what? F2 plus F2, because it's directed in the x-axis direction. So F2 times is the beta axis, no, sorry, alpha axis is this one. So what is the horizontal component? F2 times, exactly, sinus, sin alpha. Then for, what about F1? What is the sign? Plus F1 times. So F1, let me see, beta is this one. So what is the horizontal component? Sine or cosine? Sine. Sine beta equal to 0. So this is the first the first equation for horizontal equilibrium. So in any case, you will see that, for example, if from this we want to find, for example, F1, F1 will be minus F2 times sine alpha divided by sine beta. So if the negative sign appears, it means that the direction is wrong. So from that, it's not, it doesn't matter. I mean, you will change the direction even at the end, it doesn't matter. But from this expression, you already see that there is something wrong, okay? Then for the vertical direction, you have, so F2, let's assume positive axis. The direction is Y is positive if it's upward. So what is F2 is positive or negative? Positive. So plus F2 is positive because it's directed in the positive Y direction. So F2 times cos alpha. Then for F1, what do we have? Minus F1 cos beta, right? Then we have do we have something else? No? Sure? Yes, minus W equal to 0. So these are the two expressions solved. So from this second expression, we don't know actually if the sign is correct or not, because it can be. So what do we do? I would do like this. So I would first substitute F1 with F2. So I take this expression F1 and I put it in here. So I have from the second equation F2 times cos alpha minus times minus. Minus again. Please don't forget minus signs because they completely change the results. Okay? So I'm just substituting F1 into F1. So minus F2 times sine alpha divided by sine beta times cos beta equal to W. I can put W on the right-hand side. Okay? Now, F2 cos alpha plus F2, this sine alpha divided by sine beta times cos beta. Just remove this. We divide everything by tangent beta, just to simplify. And this is equal to W. So from this expression, now F2 is very simple to be found. So F2 is equal to W divided by cos alpha plus sine alpha divided by tangent beta. And this is the solution. Okay? And now, of course, this solution now is simple because you substitute this solution in here and you find also F1. So F1 and F2 now are knowns. Known. So probably one of the two, either 1 or 2, is the wrong direction. Let's assume that 2 is the wrong direction, because I want just to be on the worst condition in order to make you understand, because it's not like this, of course, but we will proceed step by step. So let's assume that, so we could conclude now wrongly, of course, and you will find out why after. We could conclude wrongly now that that F1 sorry, F2 is opposite to the assumed direction. So we could conclude, for example, that if W is this one, F1 was this one, and F2 before it was this one. Now we could assume that, for example, F2 is the opposite. So we've just changed F2 instead of that direction. We take the opposite direction. What happens? It can be right like this. Why? Ilia is asking, were F1 and F2 part of the problem, or did we assume they exist as a result of W? F1 and F2 are unknowns. And yes, they exist after the application of W. So we know there is a, maybe also this window, please. Yeah, please. There is a very bad noise outside. So yes, Celia, yes, they exist as a result of W. Exactly. So, is it correct or not, this new assumption? And what about the vertical equilibrium? Is it satisfied? Please. Yes, it doesn't matter because then at the end you will find negative. But if you want to be sure from the beginning, which is the correct, let's say, assumption, for example, this is not correct. Why? Because it was the same consideration made before for the horizontal equilibrium. It's the same, but in this case, it's the vertical equilibrium. Because if I write down the vertical equilibrium, I have that all the components times sine or cosine are in the same direction. So one of them must be wrong. So it cannot be true. Moreover, even if I don't make this consideration, okay, let's forget this consideration. It's very important, of course, you must understand it. But if we don't consider this, let's try to close the polygon of forces. So we have W here, then let's assume we start with F1, for example. Then we have F1 here. And then we have F2 with the head to tail method. Is this polygon closed? So is the equilibrium possible? So not possible. So assuming that the two elements in this case F1, so AB like F1 like this was compressed and F2 was in tensile state is not correct again. So the only way to close polygon is this one. That you start from W, then you have F1, and then you have F2. This is the only way to close the polygon. So it means that if you come back to the free body diagram, you have W, then you have here F2, and here you have F1. So if you go on the example, given example, so here you have the two elements, 1 and 2. They are both attached to the wall. F1 is in this direction. F1. And F2 is in the other direction, F2. And you have here the self-weight, of course, of the element, the given load. So that's extremely important because this is B, this is A, and this is C. It means that in reality, AB is subjected to tension. Because the force F1 is going out from node B. And BC is subjected to what? Tension or pressure? Yes, or compression. Pressure or compression. Because F2 is going towards node B. So anytime, this is very important because you can understand what elements are subjected to tension and what elements are subjected to compression. And if you go by intuition, you understand it immediately. Because if you have two elements, like, for example, these two elements, node B is this one. Node B is this one, okay? Let's assume that the wall is this one, okay? And I attach a weight from the node B like this. This element will be subjected to tension, and this other element will be compressed. Because the deformed shape will be, and now I exaggerate, it will be this one. So this element will, this weight here will tend to detach, okay, to lengthen this element. So when an element is lengthened, it means that is subjected to tensile force because I'm like making like this. And when an element is compressed, then it shortens. So it was comprehensible since from the beginning, actually, that the upper element, AB, was in a tensile state. And the element at the bottom was in compression state. So it's just a matter of like make this, this consideration. Clear for everybody?
Excuse me, Professor.
Yes.
Sorry. I have some question about the free body diagram. And the free body, the correct free body diagram is that. Can I draw the screen? Let me the screen. Let me draw at your screen because.
No, I don't understand your question. Sorry, is the free body diagram?
Yes, for example, the image is clear, Professor.
Yes, I hear you, but I don't understand your question. Maybe you can write it in chat.
Yes, I write.
Or you can try again because I don't hear you very well.
My question is that my question is that two struts must be in a tensile or in compression, or one in tensile or one in compression.
We have just seen that one is in tensile state and the other one is in compression state.
Both of them in tensile is incorrect. Yes.
Or?
Both of them in tensile is not correct. Yes.
No, it's not possible that both are in tensile stress, in tensile state.
Yes,
and therefore the equilibrium is not possible. Because
yes, not
if both would be, if both were in tensile stress, it means that the free body diagram was this one. Would have been this one. So this was W. This was F1 in tensile state. So this one, okay?
Yes.
And the other one in tensile would have been like something like this, okay? So to close the polygon, you have like W, for example, F2 and F1. So your polygon cannot be closed.
Yes. Yes.
Clear?
Yes, I understand. Yes.
So it must be in the opposite direction.
No. Yes. Thank you, Professor.
No problem. Other questions? Good. So let's take, I understand that F1 is under tensile stress, but is the direction correct also about the F2. The directions are given by the truss elements. So A, B, and B, C. So the drawing is not perfect, I know, but yeah, the directions are correct because the directions are completely defined once that A, B, and CB are defined. So the directions are given by alpha and beta. So since alpha and beta are given here, it means that the directions are correct. Okay, Torkan? Am I clear? Okay, perfect. Okay, so let's take a 15-minute break and we start then. Thank you. Yeah, sorry. Now, do you hear me? Yeah, great. Yes, Saba, okay. I'm going to send all of you the PDF notes of today, also to the online students. So you'll have everything to study for tomorrow. Especially this part will be included in the tomorrow's test. So the most important supports are three, basically, and we'll focus our attention on them. The first one, let's go from the simplest to the most difficult. It's not difficult, but let's say it impedes more rotations and more movements. So the first one is indicated like this. So there is a gap between the base, foundation, and the triangle. And sometimes you can find it in other books like this. Some other times you can find it with 3 circles, or sometimes you can find it like a small truss connected to a beam, very small truss. So this is called roller support. And this roller, I want to, I've drawn a table, which is very clear to me. And I hope also it will be for you. This roller implies no movements enabled. All 4. Yes, these are just different ways to to express it. But the one that we will use the most will be this one, the first one. So this is the roller, okay? No movements, no, sorry, this is wrong. Sorry. Right, I'm tired as well. So the only movement which is impeded, let's say, is the vertical translation. So the two movements which are allowed are vertical translation, so we call it delta y. So delta y, nope, delta x and phi z. What is delta x and phi z? Let me write this plane. The plane is x and y. So delta x and fz allowed means that this point, the node connected to this support can move either in horizontal direction or the extremity of the beam connected to it. For example, this one, if this one is a beam connected, the axis of a beam can rotate. So if it rotates, it will be, for example, like this. So it can rotate. Clear? Okay. So for example, the roller, I've brought a roller in here. It's this one. This, or it's like a roller. So this is like something which can translate, but at the base, it cannot go down or up. It's like fixed in vertical direction. It can only rotate like this and translate in horizontal direction. Okay, so it's a roller. And therefore, what kind of reaction forces do we have? The reaction forces is just one. So we have two movements allowed and one reaction force, different from zero. The reaction force is in vertical direction. Okay. So the second one is the pin support. It's represented like this. It's very similar to the roller, but the only difference is that it's fixed on the ground, so it cannot translate. So it's called pin support, or also hinge. What is allowed? It is allowed only phi z, so the rotation around the z-axis, which is the axis perpendicular to the plane. So, for example, a hinge is this one. This element is fixed. You have to imagine it fixed on the ground, and the elements connected to it can rotate. So this is an hinge. Okay. So phi z is the only movement allowed. is the rotation. And in this case, we have two reaction forces different from zero. The two reaction forces are vertical reaction force and horizontal reaction force. The third element, so this is the second one. The third element is this, is the so-called fixed support. Or encast also. Here, no movements are enabled. So anything can be, this point is fixed, you cannot move it. And therefore you have three reaction forces different from zero, which are the vertical reaction force, the horizontal reaction force, and the moment. So the fixed support cannot even rotate. So the fixed support is fixed. That the beam extremity, if it's connected to a fixed support, cannot rotate. An example is a balcony. So you can have, for example, like a balcony connected to a fixed support. You can have people on the balcony, so some weight on the balcony. The deformed shape will be this one. So you'll have a deflection at the free end, delta, let's call it y, uy, a deflection, doesn't matter the symbol. But at the fixed support, you see this point, the A point, which is the fixed support, doesn't move. Also, it doesn't rotate. So it means that in the deformed shape, you have that the angle, if at the beginning the angle was 90 degrees, after the deformation, it remains 90 degrees. So it remains 90 degrees, the fixed support. So in other words, the fixed support absorbs vertical, horizontal, and moment reactions. So we have all these reactions in the fixed support. Okay, so this table is very useful, in my opinion, because then you can directly understand. And it's nice also to remember, because if you remember that in a plane, how many degrees of freedom do we have? An object, for example, this notebook is in space, okay? Is in a plane, sorry. So it cannot move like this, for example. It cannot detach from the desk. It must stay on the plane. So how many movements it can do if we fix a reference system? One movement is yes, Yeah, it can move. In the x-axis, for example, so horizontal translation, then vertical translation and rotation. So let's assume that the desk is vertical. So you can move it in horizontal direction, in vertical direction, and rotation. So in a plane, you have 3 degrees of freedom. Oh, sorry. 3 degrees of freedom in a plane, which are the translations delta x, delta y, and phi z. Sometimes I prefer to put just phi because z is, I mean, implicit. So you have 2 translations and 1 rotation. So anytime you have a body in a plane, you can have these 3 degrees of freedom. So total is 3. With these supports, so remember this number 3. So with these supports, for example, roller has 2 movements allowed and 1 reaction, total 3. The pin support has 1 movement allowed and 2 reaction, total 3. Fixed support has no movements enabled, 0, plus 3 reaction forces, total 3. So the total must be always 3. So the reaction forces correspond, this is important, I write it down. The reaction forces correspond to the impeded movements. In other words, indeed, the reaction forces appear when there is something which must be blocked because it's a support. So if you have, for example, the hinge, okay, so you have this, you have 2 hinges, for example, in this beam. So the free body diagram will be, and you have maybe like a load P at mid-span. The free body diagram will be the beam itself with the applied force and the reaction forces. So the reaction forces will be these ones in principle, the purple ones. Yeah, thank you also who answered from home, okay? So we have, so in principle we have, we can say that the movements which are impeded, so for example, for the hinge, the vertical translation and the horizontal translations, translate, sorry for the play of words, I mean, that they translate into the corresponding reaction forces. Because if I have to impede a movement in horizontal direction, I will have a reaction force in the same direction. Otherwise, the movement cannot be impeded. Okay? So is that clear? So this table must not be learned by heart as any other things, thank you, in this course. It must be understood first. Then we can learn something by heart, otherwise no. Okay? Do you have some questions? Okay. Let me check if I can introduce something else or we finish like this, because I see you particularly tired. Really tired. Yeah, let's just give the definition of statically determinate structure, okay? Starting from this consideration. So if I add a roller, if I add this roller removes 1 degree of freedom. We can look at also from this perspective. The roller removes 1 degree of freedom, which is this degree of freedom. The line of action of the roller is always the line of action which is perpendicular to the ground. So which is the degree of freedom which is removed? No. Why? Yes, because in this direction it can move. So the freedom is allowed, let's say. So the degree of freedom which is removed is delta y. And therefore, we have one, we can call it restraint. So R is equal to 1. If R is a restraint, generic restraint. Because it restrains the motion in this direction, in the vertical direction. The pin support or hinge removes how many degrees of freedom? 2. Exactly. 2 degrees of freedoms, which are? Yes, Ain, correct. What are the degrees of freedom removed? Delta, yes, x and y, yes. Delta x and delta or delta y. So how many restraints do we have? 2. So we have 2 restraints. So R is equal to 2. Because vertical translation and horizontal translation are blocked. It cannot move. That point must be fixed there. It can only rotate. So it can only do like this. So the line of actions are horizontal and vertical. 2. They are 2 now. And finally, fixed support removes how many degrees of freedom? 3. Delta x, delta y, and phi. So we have 3 restraints. R is equal to 3. Okay? Okay. I think we can stop here because it's better, okay? So tomorrow we'll start as usual at 9 sharp, okay? And so bring your laptop and study, try to study.